So, hello guys, very good morning. So here we will be starting our the new particular topic, that is theories of failure, and we are continuing our series of strength of material. This is our lecture number 7, right? This is the first part of the theories of failure. One more lecture will be there in which we will be covering remaining theories of failure, right? So before starting the basically this topic, I would like to tell you some of the important basic understanding why we need these theories of failure, right? Now, before answering that question, why we need theories of failure, before that, we have to answer that how many types of the total, how many theories of failures we have, right? Under a static load. Right? Static load means gradually applied load. You can consider all the whole strength of material, whatever the load is applicable, whatever the load has been applied, this load. This is not a suddenly applied load. This is a gradually applied load, right? This P is a gradually applied load, and that classify under static load, right? So generally, why we need theories of failure? Before answering that question, we would like to take what are all the total types of theories of failure we have, right? So here we have the 5 types of theories of failure. First is maximum principal stress theory. Maximum principal stress theory, that is also called as normal Rankine's theory, right? That is also called as Rankine's theory. Second theories of failure we will be having as maximum shear stress theory, maximum shear stress theory, also known as Guest or Tresca's theory. Right? Third theories of failure will be taking into the picture is as maximum principal strain theory. It is also known as Saint Venance theory. Right? For your gate examination purpose, it is least important. Right? Not that important. But I'm not saying that question cannot be asked, but question can be asked. But I'm saying that regarding practicing the question, suppose you are practicing 10 problem or 20 problem regarding the Rankines or other theories of failure, you just practice 2 or 3 problem regarding this maximum principal strain theory, right? So in our lecture, we will be covering these two first. That is in the lecture number 1 of theories of failure, we will be covering Rankine's theory and Tresca's theory. The lecture number 2, I will be covering this remaining 2 theories of failure. That is a maximum strain energy theory. We also call Higgs theory. And the last one will be maximum distortion energy theory. That is also called as Hanke's or von Mises theory, right? So these are the basically, we have the categories of types of failure, theories of failure for our strength of material. Now, before moving on to the first one, that is the Rankine's theory, we would like to take why we need the theories of failure. What are the physical significance of theories of failure? It will take 5 to 10 minutes, but it is very important. At least why we are studying the topic is very much important, right? Now, so theories of failure, I'll be denoting by TOF in short format. Now try understanding. In this theories of failure, why we need this different types of, not only one theories of failure, 5 theories of failure, right? So why we need that, that is what the point of discussion. So if I just take the example number 1 in front of you so that you can understand, this is a bar with, I have applied the load P to this bar like this. That is a axially applied load, centrally applied load, central axial load that has been applied, which is having a length L. Bar is having a diameter D, for example. And suppose we got the yield strength of this material as 250 megapascal from the universal testing machine. We got yield strength of the material as 250 megapascal, right? Like, now, what is the yield strength and all? You need to just go back to the basics of stress versus strain diagrams. Now here, if you just plot, you will be getting something like this. So this is my different, you will be calling as yield strength, right? This will be your ultimate. You no need to bother so much about this curve, but I'm just telling you for that, understanding purpose. And this is the failure stress. This is a typical stress versus strain diagram for the mild steel, or you can say ductile material, I would say. Ductile material, right? So if it is reaching beyond this yield point, point number A, if it is reaching beyond that, we consider this is as a failure point with respect to strength of material, right? Now, so this yield strength, whatever the values there, they have given into the what question itself, and we need to find the diameter, my dear friend. We need to find the diameter. What are all the values of diameter that we need to calculate? So we know that maximum stress which is being generated into this material has to be less than permissible value. Has to be less than or equal to permissible stress value. Sir, what is the maximum stress? Everybody know that P divided by area. Should be less than or equal to what? Permissible. What is the permissible stress? Failure stress. This will be considered as failure stress for us. Divided by my different factor of safety. So what we can write from here? We can write 4 P divided by pi by 4 d square should be less than or equal to what? 250 divided by factor of safety. Whatever the factor of safety will be given in the problem. Right. So from here, my different, what will be the diameter? The diameter has to at least has to be greater than or equal to 4p into factor of safety divided by pi into sigma by t. So my dear friend, you are so sure about calculation of the diameter once you know the yield strength of the particular material, right? Once you know the yield strength of the particular material, then only you can able to calculate diameter. Then only you can calculate the diameter, otherwise you cannot calculate. That is as simple as that. But what if I give the complex state of stress loading condition like we have discussed in the principal stress? If I just take the example number 2 in front of you, you will understand what I'm talking about. If you just consider same bar, same length, same diameter, same axial load, everything is same. I have applied the load P, axial applied load, and I have applied the twisting load also like this. Twisting load. Apart from axial load, I have applied twisting load. So at any point, if I just take the stress element, and if I'm going to make sigma x here, and of course, we're going to take tau xy, something like this. So it is a complementary nature. So that will be something like this. So this is the biaxial state of stress, right? This is the biaxial. This is the biaxial state of stress conditions, my dear friend. Now, understand. Sigma x, everybody know that P divided by area. Tau xy from the twisting formula, 16t divided by pi dq. Now we know this, all these things, my dear friend, right? Sigma x we know, tau xy we know, right? I'll be covering the twisting chapter, that is torsion chapter soon. In that, I'll be telling you this particular formula, how it is being derived. But as of now, you just consider that the twisting formula will be 16t divided by pi dq, right? Now, so here what we are understanding, from here, that this is the biaxial state of a stress system, right? This is the biaxial state of a stress system. How to calculate the diameter for this case? For this case, we cannot say. For this case, we cannot say that yield strength will be directly considered for our calculations, right? So for this loading condition, unavailability of failure stress, right? For this loading condition, unavailability of the failure stress leads to need of theories of failure. Now, right now, I'm not disclosing so much about this statement. Once I will discuss each and every theories of failure, then you will try to connect the dot between this slide and whatever the future slide will be there. And that is what the motivation for us to keep continuing this particular lecture, right? Now, so for this typical loading, for the combined loading case, I would say combined loading case, we don't have the failure stress. For this combined loading, we don't have a failure stress. Then how to proceed with that? So theories of failures we're gonna use, right? In that, the first category will be the first types of theories of failure we do have is maximum principal stress. We also call maximum normal stress. We also call this to be a Rankine's theory. This is very much suitable for the brittle material. So maximum principal stress or brittle, this Rankine's theory is basically suitable for brittle material. Why it is suitable for brittle material, we will see, right? This is an important point. It is not that much suitable for ductile material, right? Now, what is the statement of this particular theories? This particular theory is saying that elastic failure or yielding occurs at a particular point in a member when the maximum principal stress or normal stress reaches the limiting strength of the material, in a simple tension test, irrespective of the values of the other two principal stresses value. Now, what is the meaning of this? Let me explain this. First theory of failure, maximum principal stress theory or Rankine's theory. Try understanding. So at a particular failure, when the sigma 1 under combined loading case, sigma 1, what is the formula for sigma 1? Everybody know that. Sigma x plus sigma y by 2 plus or minus under root of, plus we are writing for sigma 1, sigma x minus sigma y by 2 whole square plus tau xy whole square. This is the particular formula we do have for this calculation of sigma 1. So it is considering all the combined loading cases, right? Sigma 1 when it is more than sigma yt, or the failure stress, then we say the failure will happen. That is the meaning of a statement. What is the statement? See, elastic failure or yielding occurs at a particular member, at a particular point in a member when the maximum principal stress sigma 1 reaches the limiting strength of the material in a simple tension test, irrespective of the values of other two principal stresses, right? What is the limiting strength of the material? In a very, very simple tension test, sigma yt in case of ductile material or ductile material. And for brittle material, we don't have yield strength, we have ultimate strength. Then the failure will happen, right? So this is one of the very, very important point. Same thing written over here also. At a failure, when sigma 1 is more than sigma y, then the failure will happen, right? Or we can write sigma 1 is more than or equal to sigma yt divided by what? Factor of safety, right? If sigma 1 is more than permissible value, this is what? Permissible value. Permissible value of the stress, right? Sigma u is what? Ultimate stress. FOS is what? Factor of safety. But my dear friend, my question is, this discussion will be valid, all this discussion will valid. This particular discussion will be valid for sigma 1 more than sigma 2 more than sigma 3. What we are writing? Sigma 1 is more than sigma 2 more than sigma 3. Right? This discussion will be valid when sigma 1 is more than sigma 2 more than sigma 3. Right? Because you might have seen in the principal stress, mathematical wise and the magnitude wise, the things are very different in case of principal stress. The principal stress are defined mathematically, not basically intuitive way of designing, right? Means what I want to say, suppose you have 20 minus 50 and 0. If I will be asking you at this point of time, what is sigma 1 major principal stress, you have to tell 20. Minor principal stress, what you have to tell? That is 0. The least value will be what? Minus 50 megapascal, my dear. So the least negative value, the larger negative value will be what? Least, or we say minor principal stress, right? Major principal stress will be the larger positive value, the larger positive values, right? Don't put sigma 1 is equal to what? Minus 50. That is a blunder. If you just want to have the reference approved, you can just go through the Gere, whatever the Gere book is there in that principal stress chapters there. There they have mentioned very clearly one line that it is being defined mathematically, not basically design way. Get it, Mamad? So this is a very, very important. Please make a note of it. Very, very, very important. These points. Now, but my question is, what will happen when the things are not same like this? Or you can say here, for this particular scenario, what will be our maximum normal stress theory? So maximum normal stress theory will be maximum of mod of sigma 2, mod of sigma 3 has to be less than or equal to what? Sigma yt divided by factor of safety for safety condition. That is the maximum normal stress theory or Rankine's theory. So if you just want to know that, always sigma 1 will not be the larger one. It can be anything. So accordingly, we have to design it, right? So very wrong statement has been framed that, you follow many of the textbook, you will observe that they always written maximum normal stress theory to be something like this. But this is an incomplete statement. That's a complete statement. This above one discussion will be valid. I told you, right? For sigma 1, sigma 2, sigma 3, among that, if mod value must be like that, that means something like this 20, 10, and 0. If these are the values, then you can have the discussion that sigma 1 will be 20, and accordingly, you have to design the according to what? Rankine's theory. But if the things are not like that, you have to modify your statement. That's a complete statement, I must say. I need to keep in your mind, right? So we will solve some of the numerical. Before solving the numerical, I would like to tell you some of the safety region according to maximum normal stress theory or Rankine's theory, right? SYT is what? Yield strength. We generally used to write like this, sigma YT or SYT, yield strength. Yes. Now you try understanding. This is a symmetrical square cross section. The shape of the safety region. See, what is the meaning of safety region? After loading condition, point should lie within this region, within this safety region. If it is lying beyond this safety region, if it is lying beyond safety region, if it is lying beyond safety region, then it is going to be fail. If it is lying beyond the safety region, my friend, it is going to fail, right? This is a symmetrical square shape. And this is for what? Ductile material. Because for ductile material, whatever the SYT is there, almost equal to what? SYC. Yield strength in tension, yield strength in what? Compression. Yield strength, this is in tension, yield strength in compression. Getting my point? For ductile material, we do have like this. But if I just say for brittle material SYC is more than SYT, then you will be having the shape will be like this. Try understanding. This will be SYT. This will be SYT. This will be SYC. This will also be S by C. Sigma 1, sigma 2. So what you can say by different, this is nothing but unsymmetrical. What do you say? Unsymmetrical square shape. Unsymmetrical, unsymmetrical square shape. The safety region would be for brittle material would be something like this. Right? Make a note of it. Very, very important. This particular theories of failure is not that much of suitable. That much suitable is not there. Suitability condition is not there for the ductile material because it has considering only sigma 1, right? And they are talking in terms of only sigma yt, sigma yt and sigma ut. But generally the ductile materials are very, very strong in tension. They are very, very weak in shear. If they are very, very weak in shear, we must consider the maximum shear stress value for our design point of view. That means we should talk in terms of what? S by S. But they are not talking in terms of that. So it is very much suitable for brittle material, but not for ductile material. Right? So these are some of the important points regarding this first theories of failure. And now we will solve some of the good numerical based on this particular fundamental topic. Now, when you try to see this question, my dear friend, this question is a very important question. A body, what is the solution? Just check it out. A body is under action of two principal stresses. 40, they have not mentioned anything about sigma 1 and sigma 2. We have to write down according to data. Sigma 1 will be what? 40. I told you. Maximum larger, maximum what? The positive values of stresses will be considered as major maximum principal stress. Major maximum principal stress. Getting my point. What about sir sigma 2? 0. The least value, whatever the most negative value, will be considered as minor principal stress. Minor or minimum principal stress. Yes, that is a blunder you might be doing for so many years that you are not aware of these things. But you read that Gere book, you will find this thing. The definition of the major or maximum principal stress, minor or minimum principal stress. Yes. We have to determine the values of the factor of safety based on the elastic limit according to 5 theories of failure. But instead of that, we are focusing our attention on what? Rankine's theory, and we will just finding the values of what? Factor of safety by Rankine's theory. Let's see. Let's focus now. So, what is the according and what they have mentioned? If the elastic limit in simple tension as well as compression is this much, right? And the factor of safety they have given, Poisson ratio also they have given, right? So we need to find the factor of safety according to first theories of failure, that is a Rankine's theory. What is the Rankine's theory? How we can able to find? What is the yield strength? Yield strength in tension and compression. They are saying that both are same. That is 200 megapascal. In tension and compression, they have clearly mentioned that it is gonna same. It is gonna same, right? So what we can just say, mod of sigma 1, maximum of sigma 1 mod of sigma 2 mod of sigma 3 should be less than or equal to what? Sigma yt divided by factor of 50, right? So maximum of sigma 1, 40, 0 and 70 should be less than or equal to what? Sigma yt you take, sigma yc you will say, sigma yc you will say, both are having same value, 200 divided by factor of 50. From here, my dear friend, 70 is equal to what? 200 divided by factor of 50. Factor of safety would be what? 200 divided by 70. And my dear friend, you will be getting what? 2.86. That will be the answer. If I would not be telling you this particular statement or story, you might be putting the values like 40. That is equal to 200 divided by factor of 50. And the factor of safety would be what? 5. And that is a blunder in gate examinations. That is wrong. Right? Make a note of it. Very, 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 very important. Now, try to solve this some other numerical based on this. This year only they have asked in GATE 2022 only in aerospace for 2 marks. On the basis of what? Maximum principal stress theory, Rankine's theory. So at any point of time, you cannot avoid any topic in GATE exam, especially in the GATE examinations. You might be preparing for some other examination, then you can ignore any topic. But for GATE, even a slightly less important things will be coming in GATE examinations. They don't bother about whether you're focusing your attention on this silly topic or not. They're gonna frame the questions. A 0.5 meter long thin wall circular shaft of the radius 2 centimeter. It is being applied axial load and the torque at the tip. The what is the allowable stress under uniaxial tension is what? 100 megapascal. According to maximum, this particular problem I will be solving after discussion of the what? After discussion of the pure torsion chapter, right? So I'll be just discussing this one. Now, not on the second theories of failure. Very, very important. That is a maximum shear stress theory. We also call this to be Guest or Trescas theory. One of the very, very important topic. The elastic failure, what is the statement? Note on the statement. The elastic failure occurs when the greatest shear stress reaches the value which is just equal to the shear stress at the elastic limit in a simple tension test. When it is just equal to the shear stress at the elastic limit in a simple tension test, right? It is basically applicable for ductile material. And now if you just focus your attention, when sigma 1 is more than sigma 2 more than sigma 3, you will find the tau max formula. Tau max formula will be what? Sigma 1 minus sigma 2 divided by 2, right? Tau max, we have another formula, sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2. And accordingly, if you just calculate, you will be getting what? Tau max is more. So from here, what you will write? From here, you will write tau maximum will be what? Tau at the failure point, if tau maximum is more than tau yield, how to calculate the tau yield value? In a simple tension test, how to calculate tau yield value? We know sigma yield value, sigma 1 minus sigma 2 by 2. But we know that in a simple tension test, we are applying only uniaxial tension, right? So sigma 1 will be what? Sigma by t, sigma 2 will be 0. So tau yield value will be sigma yt divided by 2. That is the failure stress for, say, basically when the twisting has been applied. This is the failure stress when the twisting has been applied. If tau maximum, if it is reaching beyond the values of what? Tau yield, we say failure will happen. And accordingly, you can calculate the factor of safety. But this discussion will be valid, I told you, when sigma 1 more than sigma 2 more than sigma 3. This discussion will be valid. This particular discussion will be valid when tau maximum, when sigma 1 is more than sigma 2 more than sigma 3. But if not, as we have seen in our previous case, if that not will be the situations, then what could be? Put a note. Note on the very important points. In general, the maximum of, in general, the maximum of, in general, the maximum of, what you can just write sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2. If it is basically what, less than or equal to tau yield stress divided by factor of safety, then we say the material is what, safe. Our discussion is valid when sigma 1 is what, more than sigma 2 more than sigma 3, but that is not the always case, you know. That is not the always case. That is not the always case. I told you, right? Now, so this will be the basically statement of what, maximum shear stress theory, my dear friend, right? And this is a failure region. This is what we have, safety region. Sigma 2, sigma 1, these are the axes we have, ordinate and abscissa. And when you plot it, you will be getting what? This will be the safety region. This would be the safety regions. The first and the third coordinates look very similar to what we have discussed about the maximum normal stress theory, but the second and fourth coordinate will be slightly different. Slightly different. Right? So this particular plot has been plotted for factor of safety equal to 1. Factor of safety equal to 1. You will see the numerical, then you will realize the importance of this particular theory. Same problem. I'm just taking the same particular problem. Same particular problem we are taking, and we are just removing this part. And yes, same problem I'm solving by Trusca's theory. Now, just focus your attention. Just focus. So what you will be getting? According to maximum shear stress theory, what is the tau max? Maximum of what? Sigma 1 is what? 40. Sigma 2 is what? 0. Sigma 3 is what? Minus 70. So maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2 should be less than or equal to what? Yield strength divided by 2 into factor of safety. Getting my point? Should be less than or equal to what? What we have written, my dear friend? We have written that is equal to, that has to be equal to tau yield only, no? Tau yield divided by factor of safety. Tau yield, what we have calculated in a simple tension test, sigma yield strength divided by 2. That is what we have calculated, you know. Now, so maximum of sigma 1 40 0 by 2, 0 minus 70 by 2, minus 70 minus 40 by 2 should be less than or equal to 200 divided by 2 into factor of safety. And what you will be getting, my dear friend? 20, 35, 20, 35, what you will be getting? 20, 35, that is what, 55? Should be less than or equal to 200 divided by 2 into factor of safety. So what will be the factor of safety? 100 divided by factor of safety. From here, what will be the factor of safety, my dear friend? 100 divided by 55, you will be getting 1 point, what? Just calculate. 100 divided by 55, 1.818. That will be the answer. So if you simply written this statement like maximum, whatever the statement like sigma 1 minus sigma 2 by 2 should be less than or equal to, suppose you might have calculated 200 divided by 2 into factor of safety, you might be getting answer as 100 divided by factor of safety will be what? 5. That is a wrong. So try to focus on the general statement of all the theories of failure which I'm gonna give, right? So that's a very, very important thing, right? So thank you all. We'll be discussing the next particular lecture, that is on theories of failure. Once again, we'll talk much in detail about the Higgs theory as well as the von Mises theory. Thank you all.